So welcome everyone to the Wasm track of Zurich. I would like to introduce to you Cheng Shao, that many of you might have heard of, but maybe not from the top of your head can remember where from. Cheng is actively involved in the GHC development and has written quite a few blog posts on the Tweak blog about Wasm. I think in the past 3-4 years, whenever I heard exciting news about Wasm in the GHC ecosystem, it was always Cheng that was the culprit. Also, it's very exciting to have this talk delivered by him in person, because Cheng is a bit reclusive, and that therefore it's a good opportunity to get to know him and his work. So take it away, Cheng.
All right, everyone, can you hear me? All right. So my talk today, or the title of my workshop, is Ingredients for Cooking Haskell Wasm Apps. And I expect some of you, if you are bringing your laptops, you are more than welcome to get started by checking out a repo that I've been posted on Haskell Wasm org. So all the slides materials and all the codes are in this repo, which is now made public. And the structure of this workshop is going to be divided into 5 different lessons, so they will cover individual topics that I would like to discuss. Each lesson will come with a small demo to demonstrate some of the features in the GHC Wasm backend. So in principle, everything that I talk today should have already been covered in the GHC user manual, but of course, text is one format, and talks like this is another format. And I hope that if you find some of my talk material to be missing in the GHC user manual, please, you're more than welcome to complain about it, and I will be improving the manual. And I will not be covering all the implementation details to the RTS level. So if you are interested in the technical details in like the code generation or how the runtime works or how the cross-compilation works, I have a talk at Haskell Implementers Workshop 23, so you are also welcome to check out that talk. Today's talk is going to be focusing on the raw ingredients. Raw, which means that we are only going to be using what's already provided by GHC Wasm backend and also Cabal, and not higher level frameworks like Miso, Reflex, or JSaddle. Well, in a production app that you're writing for your company's frontend, you will probably want to start with a more established framework like Miso or Reflex, because they are already tested to work with Wasm. But I figured that it would be nice to keep this talk neutral to frameworks and make it stick to lower level primitives. And regarding questions, you can ask live questions during the talk, but for me, it's better if you ask it in the Discord Wasm channel. So I will be keeping an eye on the Wasm channel, and I will repeat your question and then answer it accordingly. So that works better than passing mics around. So let's start with lesson 1, your first Wasm module. Let's build the point-free command line app, because we are Haskellers and we want to look smart. So compared to wasting our neurons to come up with Lambda binder names, it would be better if we can just stick it into the point-free CLI and come up with some code that, well, may look less readable, but makes us look smart anyway, right? So here, I have a checkout of the Zurich 2025 repo in my laptop. You can use Nix develop to bring up a development shell, which includes all the tools necessary to hack everything in this repo. But if you're not using Nix, you also have other mechanisms for bringing up the dev environment. Check out the README for details. So here, I'm in the Nix shell. I'm going to the lesson 1 directory. And in the lesson 1 README, we already have a command to build the point-free.wasm module. So let's do that. Just copy-paste it. Right, because I already have my local Cabal cache ready, so it builds instantaneously, but I can assure you that it builds pretty fast on your laptop too. So now we have point-free.wasm But what does that mean, really? So, right, you can use Wasm 32 WASI cabal to build the point-free executable component. In order to figure out what a Wasm module really means, the best way to do it would be to disassemble it to a readable text format and take a closer look. So in the development environment, there is a standalone tool called Wasm tools, which can do a bunch of things like converting between the binary format of a Wasm module and the textual format. So here I'm printing it to the textual format, and let's take a look in the editor. So there is a lot of stuff, and to figure out all the concepts, even the higher level concepts in Wasm would probably exceed the scopes of this exact talk. So let us focus on the 3,000-foot view on Wasm. So what is Wasm actually? We have all heard of the advertisement of write once, run anywhere, right? It has been repeated multiple times. We have ActiveX, we have Java applets, we have Flash, and all these things. And we keep reinventing the wheel, but I think we are doing it the right time this time, because Wasm is rather low-level bytecode format, and it is properly sandboxed, which means that, well, you can run it in a variety of environments and only using the capabilities you are granting it so far. So there is much less worries about sandbox escapes and whatsoever. And a quick look at the disassembled modules, we will see that it starts with a type section, which defines all sorts of type signatures. We have rather primitive type systems that only consists of the integer types and floating point types. We also have a type regarding the external references, although I will not be covering it in great details. And now, a very important section is the import section. So you see that Wasm itself is just an instruction set for doing pure computation. And in order to do anything useful, like even just reading the system clock, would require it to access the functionality through an imported host function, so that we are importing a variety of functions here in the WASI snapshot namespace, which is a very stripped down subset of the POSIX things. And also, we have a linear memory. So a linear memory is just like the memories that we have in the conventional instruction sets. It's just a flat buffer with bytes, zeros and ones, and you can do memories, loads, and stores. But in a JavaScript environment, this memory would be backed by a growable array buffer. And we have globals, although that is not implementation details today. And another thing is exports, because in order for the Wasm module to be useful to the outside world, we have to perform some computation and observe the results, right? So this is the simplest export so far. So we are only exporting a start function, which is sort of like the main function in a conventional command line interface. And then we have all the function definitions here, and I don't think we need to go through the definitions of all the Wasm opcodes here. So, right, so this is actually the high-level concepts we are going to be needing today. We know the linear memory is just a fat buffer without any fancy things like mmap and such. It's just zeros and ones. We have import and export functions. And one thing I would like to mention is WASI, because, you know, WebAssembly itself is a pretty portable standard, but what functionality you can grant to a Wasm module is less portable, and implementations may choose to expose different levels of functionalities to Wasm. So a few key players in this space are assembling together and putting out a standard called the WebAssembly system interface. So this is just a standardized API that we provide to the Wasm module so that it can do things like reading the system clock, getting entropy for its random number generator, or doing the input-outputs of basic file system operations, except the file system is going to be a virtualized one. You have to explicitly map some of the host files there, or just make it purely in-memory and virtual. And finally, there is the module and instance separation between in a Wasm module's lifetime. So when you load a Wasm file from disk, you have to do some just-in-time compilation so that it becomes a stateless piece of machine code in the memory. So that is what we call the Wasm module. And one Wasm module can be instantiated many times. So each instantiation will create a Wasm instance with its own copies of the linear memories and etc. And then you can interact with this instance by calling some of the exported functions and getting the results, and also observing the changes in the linear memory. So this is what we all need about the Wasm module in this workshop. So how do we run it? This time, we are generating a simplest Wasm module, which is self-contained. It only relies on the WASI functionality. It doesn't have JavaScript FFI, so which means that it is portable, and it can be run in a non-web embedder as well. So we are going to be using Wasm time to run it. We have this way to pass the Wasm file, and we can also pass the command line arguments, like we can pass help, and okay, point 3 says we can pass the expression via standard input. So let's do that. How do I do X, Y? All right. It's outputting an expression that doesn't make us look very smart, so I'm going to be trying something more complex. X, Y, Z. Sorry? Zooming? Okay.
Increase the font size.
Zoom in. All right, how does it work? Okay. All right, so right now it outputs an expression that I totally can't understand in like 30 seconds, but makes me look smarter because it doesn't have any lambda binders, right? So the point3.wasm executable now works in Wasm time. We have confirmed it. And if you're using any JavaScript FFI anywhere in your stack, then Wasm time doesn't support that currently, so you have to run it in a browser. And now we can run it in a browser or some other environment that supports JavaScript. So in order to run it in a browser, we need a JavaScript library that provides the minimum subset of WASI to support. And we have now officially blessed npm library for doing these kinds of WASI imports. You can click on the hyperlink in the slides later in order to build your own apps. So I'm going to be taking you to the source code of index.html. And this is actually pretty simple. We only have a single text box waiting for the input. And then we load the npm library, and then we wait for the DOM to be ready. And then we set up that event handler for whenever the text is changing in the input box. And then we instantiate the already compiled Wasm module and then pass the expression via the standard input. So let's see how that works out. Oh, all right. All right, so it seems to be functional in my Firefox environment as well. And I would say the output speed is pretty fast. We can try a much larger expression later, but yeah, let's go with the next slide. So the lifetime of a Wasm module in browser is just compiling it, then instantiating it, and then you can do things like calling exported functions. So we can also use the WASI for doing things like virtual input-output and doing a virtual file system. But the details, you should be reading the documentation of that npm library. And I wouldn't be covering all of these in this workshop. Another topic before going to the next lesson is optimizing the size of point3.wasm, because let's take a look at how large it is currently. 8.5 megabytes, so totally a shame, especially if it is not compiled through micro Haskell, which I assume it will be much smaller. But the raw output of the Wasm module by GHC Wasm backend is slightly less optimized because we don't do a lot of the peephole optimizations that are done by other third-party tools. So we have a community tool called Wasm opt, which can be used to do a post-linker optimization of the .wasm module and output a much smaller and maybe slightly faster Wasm module that has the same runtime behavior. So let's do that. In the readme.md, we have a wasm opt command. There are a lot of different optimization flags and the individual optimization passes of wasm opt that you can use. And you can check the manual of that tool for details. We won't be covering all of those. We are going to be just doing the simplest thing here. And let's check the size right now. 3.6 megabytes, so it shrinked more than 50% while retaining the same functionality. And this is the one of the necessities when you are deploying a production Wasm apps. Yeah. And you can even use a broadly command line interface to estimate the transferred Wasm module size, because just optimizing it using Wasm opt is surely not enough. You want the compression to be applied when the Wasm module is transferred over the wire. So the most widely used algorithms these days is broadly, so you can use this to estimate the size. And we can compare the size of the Wasm modules against the native executables. So I wouldn't be starting another Docker image just to compile this to x64 Linux to compare the size, but I have already recorded the results here. The unoptimized size is more than 8 megabytes. The optimized size is 3.6 megabytes. And the native Linux executables, even when split sections is enabled, is 14 megabytes. Yeah, it would be very inspirational to try to use microHS to see how much size it will be after linking, but I would leave that to a motivated reader after that. All right. And let's go to the next lesson, go through the basics of the JavaScript FFI. So the next lesson is going to be a bit more involved. We are going to be using the HLedger library, which some of you might have heard of it, but for those of you who haven't heard of it, HLedger is a library that converts a plain text ledger and to a structured representation. And then you can use that structured representation for like pre-printing to HTML or doing some personal finance statistics, that kind of thing. So let's see how the let's build it. Sorry? I think we need to do a force refresh. All right. there is some cache issues with the warp server. So anyway, we have a text box for inputting the plain text ledger, and then our Haskell app will parse it to a Haskell ledger tree and then render it to HTML nodes below. So let's try. HLedger is capable of tracking any kinds of asset in any units, from dollars, euros, to even hours as time. So we are going to be using it as a personal time tracker. So let's see. Like yesterday, I watched anime for 1 hour. So let's track that in this. So you need now account name. And in this case, I'll just regard it as like anime, 1 hour. All right, I think this should be the correct format for HLedger, and somehow it reminds us that it can parse this plain text ledger, but the transaction is unbalanced. So the way it does accounting by default is that you have to do balanced accounting in 2 directions. So we can, in the case of time tracking, we can probably say that yes, it's canceling out because the cost center of anime consumes 1 hour of time. So equivalently, I lost 1 hour in my life, but I guess that's a rather pessimistic way of doing accounting. Yeah, I think the point of today's talk is not to cover about how to do personal finance. So here is just a proof of concept to let you know that, yes, this thing works. If you are motivated enough, you can take the source code of lesson 2 and expand it a little bit, like adding some fancy visualizations using d3.js or whatsoever. But well, here is the point is to show that we can do JavaScript FFI here. Yeah, so in order to build a front-end app in this way, we need to build a Wasm module, and we also need to build a tiny companion JS module, which contains all the JS source snippets, which is supporting the JavaScript FFI functionality. This companion module can be built using a script which is installed along with GHC Wasm backend, and you can take a look at what this source code looks like. It is copy-pasting some prelude code, which is the tiny bit of JS code required to support the functionality. And the relevant JavaScript FFI source code snippets are gathered down below, and we also have index.html. You can check the HTML source code later to see how we initialize the instance code and then call the exported functions, and we won't be going through all the details of that. So the demo code in the Haskell side is rather simple. Lesson 2.hs is just less than 100 lines of code. What it does is we have a foreign import code, which is just find the relevant table element in the HTML, and then set the HTML markup to update the table. So we calculate the markup, render it to an HTML string in Haskell, and then pass it to this foreign function. And we also export a Haskell function as a JS function, update table, so that it can be registered as an event handler. Whenever the input ledger is changing, then this function is going to be invoked. And yeah, so we are using a Lucid library for rendering the HTML markup. And we also need to cover one topic, which is the special link time options. So the Cabal file of lesson 2 is pretty simple. We have one single executable component. But whenever you are working with a GHC Wasm front-end project and uses JS FFI, then you need a few special GHC link time options. I wish some of these can be automated by some higher-level tools, but for now, you need to make sure that no HS main is enabled, because in case JS FFI is enabled, the default main function doesn't work. And you also have to tell the ALM VM linker to link it as a reactor instead of a command module. So a command module is by default what is containing a default main function, and a reactor module is sort of like a shared library in which you can export a bunch of different entry points, and once the shared library is initialized, you can call the exported entry point functions whenever times you like. And you also need at least one of these entry points, so the statically exported Haskell functions. So in our case, it is update table. So you have to tell the linker to use it as the garbage collection rules. Otherwise, if you don't include linker flags like these, then the linker is going to strip away all your useful Haskell code. So you need at least one of these. We have the JavaScript foreign import JavaScript unsafe, which the syntax is pretty simple. First, we have to cover what kind of arguments and return values can be used in the type signature directly. So the basic boxed foreign types that are allowed in the C FFI, like the integers or pointers, they are all allowed in the JavaScript FFI. But we don't support the unboxed foreign types yet, but we may someday. And another thing that we support is a magic type, which is exposed via the GHC experimental packages, ghc.wasm.prim. It is a JS file resembling the same thing in GHC.js and the JS backend. It represents arbitrary JavaScript value that exists outside of the Haskell heap because, well, the JavaScript heap is a different construct, and the Haskell heap only exists in the form of zeros and ones in the Wasm linear memory. So it's actually two different heaps. So the way that we represent JS val on the Haskell heap is that we have a tiny bit of JavaScript code for managing a unique mapping from a unique integer key to the actual JavaScript value. And then we can just store the integer key as a Haskell heap object in the Haskell heap. And we are also reusing GHC's own weak pointer mechanism for garbage collecting the JS files when they are no longer reachable by any of the Haskell garbage collection routes. And yeah, they are garbage collected on the Haskell side, but they can be eagerly freed by free JS file. And we also have a JS string, which is just a simple new type of JS file. And you are also encouraged to wrap JS val with your own new type when you are writing your own code to do the JS FFI imports. Now, I hope you are not scared away by the unsafe keyword here, because, well, we use unsafe C FFI a lot also in production Haskell code. So the unsafe keyword here is just an acronym for doing synchronous JavaScript FFI, which is the most simple way of importing a JavaScript code. So what it does is it calls a synchronous JavaScript function, blocks the entire Haskell runtime, waiting for that JavaScript function to return a value. And then that return value is used as the JS FFI imports return value. The source snippet here, it can be any valid single JavaScript expression, or if it fails to parse as a JavaScript expression, then it has to be some valid JavaScript statements, which will be wrapped in a JavaScript function body, and you can use return keywords to return the actual result here. And inspired by the GHC.js and the JS backend syntax, we are also using $1, $2, etc. to represent the first, second, and third Haskell function arguments. And the simplest form of JavaScript imports all the arguments and the results, they are fully evaluated. So there are no thunks involved in the synchronous case. And most of the time, when you are not calling asynchronous JavaScript function like fetch or etc., then you should be defaulting to use the synchronous variant of the foreign function interface. And now, we also can export a Haskell function to JavaScript using the foreign export syntax. So as I mentioned earlier, when you are using JS FFI, the default Haskell main function doesn't work. You have to pass no hsMain flag and manually specify at least one export function as the entry point. And If we are adding annotation sync here, so this indicates to the JavaScript runtime that the update table function is synchronous. It doesn't return a promise to be awaited. Once it is invoked, it will run the Haskell thread till it is completed or killed. So the synchronous form of export is useful when you want to ensure that when you export a Haskell function to JavaScript, you call that export, and it also always runs to completion before the next export is going to be called. This is very useful when you are doing animations, because if you are calling a Haskell function to draw every frame in an animation, you don't want the executions of these different Haskell functions to be interleaved, and there may be tearings in your canvas, so you need to ensure that the execution is not interleaved. So this is where synchronous export is useful. The drawback is that because we are calling a Haskell function and we cannot really block the runtime until it is completed, that means that we cannot call back into JavaScript and wait for a promise to be resolved. So you cannot call asynchronous functions like fetch and etc. So in most of the cases, and by default, an exported Haskell function is async, which means that when you are calling an async function in JavaScript, you are going to be receiving a promise that is going to be eventually fulfilled with Haskell execution or result. Or in case a Haskell exception is thrown in the main thread, then that promise will be rejected with a JavaScript exception, which contains the serialized Haskell exception results. And yeah, asynchronous exports are more preferable in this case because it enables calling async JS function in your logic, and it allows a proper error handling. And another little thing to be covered here is using GHC ID to hack on the code base. So unfortunately, we do not support the Haskell language server yet because this requires a little bit of non-trivial effort. In theory, it might work with moderate efforts because the GHC Wasm backend already supports loading code via GHCI, which means that we can use GHC ID to as the poor man's IDE here. So yeah, I'm not going to be doing all the live coding here, but just to let you know that GHC ID works. If you are wondering how to write invoke the GHC ID command, you can see it's just using Wasm32 WASI cabal repo and then passing f no code to repo options. So yeah, using GHCI is pretty simple. It's just the cabal repo command. You can use repo options to pass GHC options which are specific to GHCI. You can use multi-repo to enable the loading multiple components at once. Oh, Travis is asking, is there a reason to not tell the linker to export all foreign export JavaScript declarations by default? Well, so the way it currently works is that the Wasm LD linker doesn't really have knowledge about the higher level Haskell JS FFI exports. So we are desugaring all the code to the either C code or Wasm assembly code, which is going to be picked up by the Wasm LD. So in the future, we might implement a slightly higher level wrapper of Wasm LD, which has better knowledge when it sees all the object files which are gathered at link time. Then it will know that, well, some Haskell functions are exported in a transitive dependency of my package, and then it will be automatically added to the garbage collection route. So yeah, this might happen sometime in the future, but not right now. So yeah. And also, the GHCI, by default, it is loaded in Node.js, and sometimes you want a GHCI session that runs in the browser and has access to the DOM, etc. So GHCI browser mode also works if you pass the GHC option -f GHCI browser. And we are going to be demonstrating the browser mode in the next lesson. But for now, you know that it works. And it doesn't work with Safari yet due to a bug in WebKit. And some people have better knowledge of WebKit. And until they fix it, for now, you can use Firefox or Chrome to run it. And I also have a lengthy blog post to announce the GHCI browser mode feature, which you are recommended to check it out. Now, let's go to a slightly simpler lesson just to get your Cabal project tested, because we need to know how to get a Cabal test component to run in the context of cross-compilation, right? So here, in the lesson 3 Cabal project, we have two top-level Cabal components. One is lesson 3, and it doesn't use any of the JS FFI in its body. And another component is lesson 3-HS, which does use the JS FFI. And this distinction will make it a little bit hard to run in things like Wasm time, and you have to run it in a GHCI test loader. So this is the thing that we are going to be testing. I literally stole it from QuickCheck's Haddock page. So it is the QuickCheck 101. It's just checking a simple property that if you reverse a simple list twice, then you're going to be getting the same list, right? And we have the main program here. And the way we are going to be testing it is to, like, we can't tell it to test lesson 3. But Cabal, by default, doesn't have any knowledge about the emulators used to run executable on a foreign architecture. So we have to use a Cabal flag called test wrapper. So when Cabal runs the test suite component, lesson 3, it is going to be passing lesson3.wasm as a command line argument of wasm time. And we can see how well it works. Yeah. Great. It is passing 100 random tests. In some more advanced tests, you may want to pass some special command line arguments to Wasm time itself, like to map some host directories as a virtual directory in the Wasm module so that the test suite can do some I/O stuff. And you can check the documentation of the Cabal in order to look for other potential flags related to this, or write a simple shell script, which you can pass to the Cabal test wrapper. So we know that high-level frameworks like Tasty or QuickCheck or HUnit, they are all known to work on Wasm. I think HSpec also works on Wasm, but I haven't closely checked yet, and you're welcome to report bugs. You can use test wrapper to check it. But if JS FFI is used anywhere, you can't use Wasm time. And there are two ways to test a Cabal test component if JS FFI is involved. You can write a special complex JavaScript module that runs in Node.js, which parses the custom sections and then prepares all the imports that are not WASI. But that is very complex. And in fact, you can use GHCI itself as a test loader. So the idea is like this. You can use the Cabal repo command to load the JS component. And I'm using a -v0 to suppress the noises coming from either Cabal or GHC, so we can focus on the output of the test suite itself. And this command is just loading it in a GHCI session and then executing the exported main function. Right, so this QuickCheck test is testing the to.js string and from JS string functions exposed by GHC experimental, because we want to make sure that the functionality that converts between JS string and a Haskell string is robust, right? And it does pass the QuickCheck test here. So in your own project, you can write a simple shell script to load your main function in the GHCI and then grabbing for the output to see if it is indeed passing the tests. So yeah, we can even use this for the running the test component in the browser mode. Okay, we have another question from Martin. What is the reason to split up a project like done in lesson 3? Is it so part of the project can be compiled both with normal Cabal as well as Wasm32 WASI Cabal? There is really no peculiar reason But I guess splitting up a project into smaller pieces allow the individual pieces to be tested better. And indeed, you can some of the pieces, if they do not involve any JS FFI specific points, then they can be tested with native GHC and native Cabal as well. So, yeah. And there is one thing I forgot to demonstrate, is that the GHCI browser mode. So we have to specify which component to load. There is another question in Discord. So I ran nix develop. What do I do next? If you can enter the nix development shell, then in each lessons directory there is a build.sh shell script that you can run it, and then the dependencies can be compiled, and then you can reproduce whatever that I'm demonstrating here. So yeah. I have passed the GHCI browser flag to Cabal repo, and now the GHCI is hung up at the moment. It tells me that I should be opening an empty page to bootstrap a GHCI here. So let's see what's happening. So I have pasted the URL here, and the network shows that it is connecting back to a development HTTP server on the GHCI side and downloading and compiling a bunch of Wasm modules. And now the GHCI session is unfrozen. I can type main to execute it, but by default, in GHCI browser mode, the standard output and standard error are printed to the browser DevTools console. So we can check the console to see that the quick check test has been passed, and we can do some things like demonstrating the JS FFI import. So, for instance, we define a simple print function that just prints an integer. But this print function does not go through any of the Haskell standard output or handle logic. It directly involves the console log. So let's just print a random integer here. And you can see the integer is indeed printed to the browser console here. So if you are motivated and you want to try the JS FFI features, then compared to setting up a Cabal project and putting your JS FFI declarations in a Haskell.hs and then going through all the Cabal link time options, a better way would be just using the GHCI browser mode, and then you can just experiment with all the foreign import declarations because they all work in the GHCI browser mode as well. So, yeah. And I think we can move on to the next lesson. More advanced JavaScript FFI. And lesson 4 is a little bit more advanced, and the index.html, it loads 2 different components. So before it loads the Haskell component, it loads a service worker. So conceptually, a service worker is a JavaScript module that runs not in the browser main thread, but as a standalone worker thread, doesn't share the heap as the main thread. And service worker allows you to do some things like intercepting the fetch calls in the browser main thread. So this is what used by the ad blockers and the browser extensions. But in our case, we use a service worker script to implement a single endpoint, which is SHA-256 And it does one simple thing. It receives a post request, and then it uses Web Crypto API to hash this thing using the digest algorithm, and then returns the digested binary in the HTTP response. And yeah, this is simpler than having to spawn a development HTTP server and then using the Haskell code to do requests to that. The Haskell part is containing several different stuff. So in the lesson 4 demonstration part, the main function is driven by Tasty, the test framework. And Tasty is doing 4 things at once. So first of all, we are doing a quick check property test. We have a pure Haskell implementation of the digest algorithm. And of course, it's going to be much faster than the poor man's HTTP server, which has to involve a lot of serialization and back and forth between the browser main thread and the service worker thread. But we just want to make sure that the Web Crypto API implementation in the browser is not making any mistakes. And we are checking it using the Haskell crypto hash SHA-256 as the ground truth. So we randomly generate some byte strings, and then we check the I/O property. We hash the buffer to a JavaScript typed array, and then from the JavaScript typed array, we can do a fetch request and get the digested result. And then that result is converted back to a Haskell byte array, and then we compare it. And the next thing we are going to be checking is the performance. And we are going to be using the Tasty bench library for doing a simple benchmark. The benchmark is randomly generating little buffers of less than 1 kilobytes. And then we try multiple times in serial to issue the fetch request and then get the digested results back, and then we calculate the wall clock time of how much time in total it takes to serially do all the asynchronous fetching. But then, in real-world front-end apps, we want our front-end app to be as concurrent as possible, right? We don't want to serially wait for the previous result to finish. So another way to do it would be using the Haskell async library. So, in the GHC Wasm backend, all the existing mechanisms of Haskell concurrency, the mvars, STM, all that kind of things are working with the GHC Wasm backend. So we can just use our good old async library. And async library provides a combinator called replicate concurrently, which is just like a parallel for loop. It spawns every single one element in that list to a separate Haskell thread. And then after all these Haskell threads run to completion, it returns in the main thread. So we divide the same batch into different Haskell threads, and then we wait for all the Haskell threads to complete, and then we wait for the wall clock time to be calculated. And next, there is actually a more efficient way of doing concurrency without the Haskell threading overhead, because in Haskell, spawning a thread is very cheap, but it is not completely free. But in the GHC Wasm backend, we can actually do concurrency without the threading overhead, which I'm going to be demonstrating later how it works. So right now, we can let's do a build to ensure the Wasm module is up to date, and we can now serve it. And we can now see that the service worker has been loaded, and there is a ton of post requests down to the service worker thread. And now, in the console, we show that the full test suite has been passing in less than 2 seconds. So we know that the quick check is passing. And doing the individual fetch requests serially, it takes something like 220 milliseconds. But if we are using the Haskell async library to spawn each Haskell thread for each fetch request, then we are cutting that time by half, something like 133 milliseconds. But the lazy fetch approach does not require you to spawn a Haskell thread per fetch request, and still we get a fairly nice speed up compared to the regular fetch. And we are allocating much less memory compared to spawning each thread for the fetch request. So we can see that the tasty bench library is also outputting the memory statistics in each one of these. So in lesson 4, we are going to be learning about how to do asynchronous JavaScript calls to functions like fetch. And we are going to be showing how to marshal binary buffers between the Haskell side and the JavaScript side. So first of all, previously for simple types like int and pointer, we can just use them as ordinary value types passed as arguments and values between the Haskell side and the JavaScript side. But when we are marshalling something more higher level, like text byte string or like JSON values in ASON, then we have to know how to pass the binary buffers between the two sides. So we can take a look at the Haskell main code to see how we are defining the relevant code here. So we define a new type, JavaScript uint8 array, which is the typed array in JavaScript. And then here, we have a single function that takes a pointer and an integer, which is the location and the byte array length of the Haskell pinned array in the Haskell heap. What we do is that we use the magic keyword underscore exports dot memory dot buffer. So in JS FFI code, you can access everything in the global this binding, and you can also use this magic keyword to refer to the current WebAssembly memory object. And then you can use the dot buffer field to construct a typed array by wrapping some parts of it. So in order to refer to a certain region in the current linear memory, you can pass a pointer and you can pass the byte length, and then you can construct a new typed array in place that refers to that linear memory location. And then you can pass it to anything else in JavaScript, like passing it to a text decoder so that it decodes to a JavaScript string, or pass it to like something like JSON parse or whatsoever. In our case, we are just passing the typed array to a fetch request so that that fetch request is issued immediately. And when you are passing a buffer from Haskell to JS, always remember that you need to use a pinned byte array. And in order to pass the unpinned byte array safely, we will need to support unlifted arguments in the FFI, and we don't support that yet. So for now, better stay on the safe side. And also, you need to pay attention to the lifetimes of the buffer when you pass the buffer between the two sides. So the point is, when we do garbage collection in Haskell, the linear memory may grow because we might be running out of megablocks and we have to allocate new megablocks to extend the heap region. And the way that WebAssembly linear memory works is that when the linear memory grows, the previous array buffer that represents the previous memory state is detached. So if you do things like wrapping a linear memory buffer as a JavaScript typed array, you pass that typed array to somewhere else without immediately consuming it, like passing it in a global JavaScript data structure. Then later, when your Haskell code does some garbage collection, then that previous typed array may be invalidated and become a zero-length typed array. So this is not desired, right? So you have to ensure that whenever you pass a buffer from Haskell to JS, that buffer is fully consumed in the JS FFI code. And this is one direction of passing binary data. Another direction would be receiving binary data from JavaScript to Haskell. And we can just use the same trick here. We allocate a pinned byte array in Haskell. We pass the pointers and length here. We construct a typed array in place, and then we can use the set method to copy another typed array to our linear memory region. So this is a way of doing it. So this is the fundamental building block of efficiently moving the bulk data between the two languages. And based on the method of marshalling the binary buffers, we can marshal more higher-level constructs like Haskell text, strings, and things like async JSONs. Although I think it would be better to left as a reader exercise. I would be glad to help if you encounter some issues here. Another thing that we need to demonstrate in lesson 4 is the new language construct, foreign import JavaScript save. So what it does is it imports the asynchronous JavaScript function to Haskell, and that JS function is expected to return a promise. In our case, we are doing the fetch here, and we are using top-level await in this JavaScript source snippet because it is going to be wrapped in a JavaScript async function anyway. So await is allowed in the JS FFI source code snippet. And now we have a critical difference between the synchronous and asynchronous variants of the JavaScript imports. So we see that we are wrapping the result in the I/O monad here. This JavaScript hash via fetch function returns a JS uint8 array, but this value, when it returns in the I/O monad, it only means that we have told the JavaScript side to do this fetch request, but the result is not available yet. This return Haskell value is a Haskell thunk. The thunk is only forced later, and it blocks the current Haskell thread until that JavaScript thread is fulfilled or rejected, in which case it can be handled as a Haskell exception. And the nice benefit of it is when you are blocked waiting for a JavaScript promise, it only means the current Haskell thread is blocked. It doesn't block the rest of the Haskell runtime, so that it means that the Haskell concurrency model fits nicely with the JavaScript event loop. So, and it allows concurrency without threading overhead because you can see in our example here that the lazy fetch recommended approach, what we do is that we do the hash to JS uint array. We do the fetch requests sequentially and get a bunch of thunks, but we only collect the thunks in a list, and only after this point we sequentially force the thunks to the actual value, so that there is still some background concurrency going on in the JS event loop, and that is completely transparent to the user, and we don't have to pay for the overhead of a Haskell thread per concurrent call. So this is the preferred way of doing concurrency in the Haskell Wasm backend. And yeah, in this form, the JavaScript exception can be called as a Haskell exception. And now, actually, we are coming to the one last demonstration here. It is a two-dimensional canvas example. So what it does is it's going to be drawing a simple 3-body animation on a high-definition canvas port, and it uses the Haskell Juicy Pixels library, which is used by a lot of projects like Pandoc, to represent each frame. So let's see how lesson 5 builds and looks. Yeah, you can see that I enabled the highest level of optimizations plus a bunch of GHC options because I want to make it really fast because it is animation. So let's see how fast can it be. Oh. It's not entirely smooth, I would say, but you changed the resolution by 600. Yeah, probably. Yeah, for simplicity, I am fixing the viewport size to rather large size, the high definition size, and it could be smoother if I make the viewport smaller. And another fundamental reason that this is not as smooth as it should be is that the lesson 5 code is structured in a very simple way. Each time when we are drawing each frame in the canvas, we are calculating a large frame buffer, and then we pass that buffer to JavaScript side, and then we throw that buffer away, and then reallocate. And if you do it 60 times per second, this is causing excessive garbage collection stress. And although we do not have a lot of garbage on the heap, doing garbage collection very frequently will still hurt the fluency of the animation a little bit. So if you're using, if you're drawing production animation, I don't know what that means, probably a game or something, then you want to allocate a mutable buffer and then just redraw the changed areas in that mutable buffer and pass that to JavaScript. And I can assure you that way it will be much more performant. The animation logic here is just in the makeImage function, which takes the width, the height, and the timestamp and generates the 3-body animation. And I can assure you that I do not understand a single line of the code here because I told ChatGPT to vibe code just this single function, but it doesn't have good knowledge of the GHC Wasm backend, so the rest of the code is still written by me. So we have a drawFrame function here, which is just using the juicy pixels generate image function to generate image, and the juicy pixel image type is just a storable buffer in the Haskell heap, and we are going to be extracting that buffer pointer and passing it to the JavaScript. So that is how the lesson 5 thing is supposed to work. My fan is spinning fast. Okay, this is one last JavaScript FFI construct that I need to teach. This is a little bit confusing because although the syntax is foreign import JavaScript wrapper, it is actually a foreign export, but it is a different kind of foreign export. The foreign export JavaScript is exporting a top-level Haskell binding as a JavaScript function. But in this case, we can use this to dynamically export a Haskell function closure as a JavaScript callback. So foreign import JavaScript wrapper, where is it? Yeah. So we are exporting a Haskell function that takes a timestamp and then draws that animation to the canvas as a JavaScript callback. And once we have the callback, we can schedule the callback to be invoked 60 times each second. So this is how the foreign import wrapper works. And just like the static form of JavaScript imports, you can add a sync annotation here to tell that this is meant to be exported as a synchronous JavaScript function instead of an asynchronous one. And in this way, you have the guarantee that there is no tearing in the canvas and the previous frame has finished drawing before the next frame begins drawing. So yeah, the sync and async variants are similar to static exports. And if you are wondering about why this is called a foreign import wrapper, you can check the Haddock documentation of native GHC and see the fun pointer type for the same thing in C FFI. Yeah, if Simon in this room, he might have a better answer than me. And all right. So that is actually much shorter than I timed it initially, and these are the 5 lessons and individual ingredients for cooking the Haskell Wasm apps. And I want to mention a little bit about the intermediate terms of work that is on my plate right now. So the improvements to be happened on the GHC side is adding support for threaded RTS and parallelism. And that means that you can automatically benefit from multi-core parallelism in your Haskell front-end app without losing any existing functionality. This is a big chunk of work, and I'm still busy doing it. But I expect it to be landed sometime later this year. And also, the GHCI, if you test the GHCI browser mode and your project has a lot of high-level dependencies, you'll notice that it is a little bit slow compared to native GHCI. And that is because the way GHCI currently works is that it sequentially loads from the low-level dependencies to high-level dependencies. And I want it to be doing it a little bit faster and loading from the higher level dependencies in the beginning, so it can benefit from some concurrency here. This is tracked in GHC issue tracker also. And finally, we don't have a lot of good observability in the Wasm runtime right now, but we do have excellent profiling mechanisms in the browser for your JavaScript code. So we want to make sure that our existing event log and profiling mechanism works very good with the existing profiling in the browsers. So I'm also working towards that. And these are going to be happening in the GHC. In the user space, I have shown the fundamental techniques or recipes for cooking the more higher level libraries and frameworks, but you might probably don't want to replicate all of these efforts in your own libraries. So sometime later, we are going to be having an officially blessed library that exists outside of GHC tree, but it is doing low-level stuff like efficiently marshalling text, async, and etc. And the way that we generate a JavaScript module which is required for running a JS FFI module is a little bit raw and not user-friendly, and we wish we have the excellent usage experience like in Rust, because in Rust, they have Rust bindgen, which you can just have a high-level specification of your app, and it does all the heavy lifting and calculating the right linker flags, and we wish to have a similar tool that does you for that in Haskell. So this is also something that I'll be working on later. And later is something that I've been experimenting with personally, binding generator for TypeScript, because if you're binding a large TypeScript library, then you don't want to manually write all those JS FFI imports, right? That is a very mechanical work. And once you can parse the typing declarations of the TypeScript, then it should be possible to generate Haskell declarations for that. So you can just start calling those TypeScript libraries directly. And being able to interface with TypeScript in a semi-automatic way, I think it is a very big deal, because the JavaScript ecosystem is like 10 times larger than ours, and you can find a lot of well-supported JavaScript libraries with TypeScript interfaces. And bringing those ecosystems to the Haskell stack, I think, is going to be unlocking a lot of exciting opportunities for the Haskell ecosystems as well. So this is also something that I'll be working on. And of course, I do not know as the end user what are the pain spots or what are the other pain spots of the GHC Wasm backend, or what is missing that users would really want in the GHC Wasm backend. So come talk to me after this talk, and we can discuss together and help reshape my priorities on this project. And the last slide is more resources. So I am active in the Wasm channel in the ZeroHack server during ZeroHack, but for most of the time, we have a matrix room in the official Haskell matrix space, which is dedicated to the discussion of anything Wasm related. So if you have any questions, quick questions, or something to discuss, you're welcome to hop by in the matrix server. Oh, somebody is asking, how is the status of GHC Wasm in Nix packages? I remember you have your own flake for now. Oh, right. So the situation of Nix packages packaging of the GHC Wasm backend is a little bit unfortunate for one main reason is that the GHC Wasm backend depends on a few large external dependencies like the LVM project, WASI libc, and Node.js for running template Haskell and GHCI. And for some reasons, like we are generating enormous Wasm shared libraries that may exceed some implementation-defined limits, we have to patch the external dependencies like LVM and Node.js. And some of the patches have the hope of getting eventually upstreamed at some point, but somebody have to take the time and effort to go through the external contribution processes. I'm too busy with the GHC side of things. And some patches have basically no chance to be accepted upstream, and thus we have to maintain our own trees and own binary distributions of those packages. And they work well for our existing distribution channels through the GHC Wasm beta repo, but for Nix packages, those maintainers may not be happy happy with carrying extra patches and extra Hydra builds for all those packages. So we may have to figure out a compromise and talk with the Nix packages maintainer. Maybe they would be happy to accept the GHC Wasm backend as a special case to accept the foreign binaries directly. You just do the patch elf, or just forbid the Hydra builds, and then whoever's motivated can maintain their own binary caches. I don't know, but it's more a technical problem than a social one. So we have the GHC Wasm Meta repository as our main official distribution channel. And we also have the GHC user manual, which covers everything that I talked today with more technical details. So you are welcome to check out the manual and see if there's anything amiss. And finally, in a production app, you might want to start with well-established framework already, like Miso or Reflex. And we have the official example repos for both the Miso framework and the Reflex framework, using these frameworks as external package dependencies. And they are to-do MVC examples that you are welcome to check it out. And finally, one special mention is the JSaddle. So if you have experience with GHC.js or the JS backend, you already know that JSaddle is a library which allows you to not write the raw JavaScript FFI statement, but instead using the interfaces provided by the JSaddle library to interface with JavaScript. The JSaddle library has a backend called JSaddle Wasm, which allows you to reuse most of your existing JavaScript FFI, make it portable across the JS backend and Wasm backend, and you just have to, at your entry point of your app, use the JSaddle Wasm library to make it work on Wasm as well. So, yeah, that is actually all from today's talk, and we still have 1 hour's time, and you're welcome to hack on your laptops or just ask any kind of questions. I will be happy to answer. Thank you.
Thanks for the great demos. One thing I have experienced in the past when using GHC.js was that working with like ECMAScript modules or CommonJS modules was a bit of a pain point for integration. Do you have any plans to support integration with like the JavaScript module side of things so you could import those libraries more easily?
You mean like libraries like GHC.js DOM that you want me to support directly in the Wasm backend?
Oh, no. Sorry, to be clear, I'm just curious. For example, like let's say React. Let's say I wanted to import React into a Wasm project, but that's packaged using JavaScript module formats. Are there any plans to have tighter integration with the JavaScript module formats available?
I have to be extremely proud here. One thing that we do better than the JS backend is that we do not emit all kinds of bindings into the global this namescope that pollutes the namescope. So you can have multiple different Haskell Wasm apps that coexist because everything that gets emitted from the GHC Wasm backend is a proper ES module with proper module scoping so that they do not contaminate each other's scopes. So that indeed you can just write a single Cabal component that compiles to a React component, and you just need a little bit of shim at the React side to load the GHC Wasm code and have it function as a React component. I haven't any experience with React, but it should be possible. Yeah.
So suppose one were to have access to some other Wasm module, like maybe they used Inscriptum or something, right? And it exposes like a C-style ABI. Can I have foreign import C call declarations that coexist with the JavaScript FFI declarations? Like, does that work? Or would it work in principle if no one has tried it?
Unfortunately, with mscripton, it doesn't work because our C toolchain is WASI SDK, which uses a different API. But I think you can just include the C sources in your Cabal project or have it cross-compiled to Wasm and have it linked into the same thing. So the point is, if you are interfacing with a C library, you most likely want to share the same address space so you can pass the pointers back and forth. In which case, you have to ensure that the object files that represent that library is getting linked into the final Haskell Wasm app. So that means that you have to use the same toolchain, share the same libc, and live with the same constraints. I know the most high-level example is people are able to cross-compile the Krypton library cbits and also to use the sec256k1, the elliptic, the crypto library used by Bitcoin to support some fancy front-end app. I don't know how that works, but people have been able to cross-compile some pretty involved C libraries to Wasm using our toolchain, so this should be possible.
Excellent, thank you.
Are there any things you can do with the JS backend that you can't do with the Wasm backend?
Let's see. One edge case that JS backend does much better than Wasm backend is because the JS backend is representing each Haskell heap object as a JavaScript object, and there is one unified heap instead of two heaps, one living on the linear memory. So the edge case is that when you export JavaScript stuff to Haskell, and then you export Haskell stuff to JavaScript. In theory, you could create a cycle between the two sides, and then the cycle cannot be automatically garbage collected because either side doesn't know about the other side's garbage collection routes. So in this case, in Wasm backend, when you create cycles like this, you have to manually break the cycle by freeing one of the callbacks when you know that callbacks is no longer going to be available. In practice, I think that is seldom the case because most of the demos that I've worked with in the GHC Wasm backend doesn't require this kind of excessive cleaning up of the JavaScript references. Another reason, although not a technical one, but a social one, why people may prefer the JS backend is that they already have plenty of experience with GHC.js, and they want to port their existing apps, which may use things like GHC.js DOM or things like that, to the JS backend. Then, using the new JS backend would be much less effort than porting it to the Wasm backend. Admittedly, yeah.
Thank you.
Thanks, that's been an amazing effort. Quick question, has anyone tried using something like Wasm VK or something else to run this on a GPU with hardware acceleration?
Sorry, can you repeat your question?
Yeah, has anyone tried using something like Wasm VK or something else to run this on a GPU?
To run it on what?
To run on GPUs.
I don't think somebody else tried it yet.
Are there any more questions? Yep.
Do you have an idea of what the performance is like compared to native code gen?
Sorry, what code gen?
Native code gen, GHC's native code gen backend.
Yeah, actually, we have a native code gen for the Wasm architecture. So that works similarly to the x86 code gen and ARM code gen and such.
Sure, but do you have an idea of the performance of running code generated with the Wasm backend compared to generating object files?
I haven't profiled it closely yet, but I assume it will be much faster because actually we do much simpler stuff in the Wasm backend codegen. We just take the raw CMM generated by the previous pipelines, and then we just emit, we do a simple relooper algorithm and then emit the Wasm assembly directly. We don't do any of the optimization passes that is done in the other backend native code generators.
Thanks. I was thinking more of the runtime performance rather than the compile time performance. If you have any rough numbers, that would be.
I don't have a quick numbers about the overhead of compiling stuff to Wasm compared to the native, but yeah, I think it will be in that acceptable margin. Yeah.
Earlier, when you run some tests using Tasty, for example, and also using foreign function interface, did I understand correctly that in this case, GHCI helps?
Yes.
The browser GHCI.
It depends on whether your JavaScript FFI is using code that is only supported in the browser and not in Node.js. If you're just using standard JavaScript stuff that is working in Node.js, then I think using the default Node.js mode is going to be easier. When you are running tests in CI, then and you are using the browser API, then you have to take extra care to set up headless Chrome or Firefox instance in order to run the GHCI browser mode. That is definitely possible. We have official support for using the Puppeteer or Playwright library to set up the headless browser instances.
But why is GHCI even still involved at that point? Couldn't you just run the entire test suite in the browser, in the headless browser?
GHC, the compiler itself, doesn't run in the browser yet. Yeah.
But couldn't you compile all your code to Wasm, then compile the test suite to Wasm, and then run that in the browser?
Yes, you can compile your test suite to a Wasm app and run it in the browser. It's just that you have to figure out all the correct cabal and linker flags and all the HTML to load that kind of thing. So yes, it's definitely possible. It's just that using the GHCI browser mode allows you to just have a main function as the entry point, and then you just load that main and forget about all the linker flags and such. So it's a slightly easier way of doing it.
Ah, thanks.
Hi. So if I remember correctly, the GHC.js codebase skips the C++ phase of the pipeline. It goes straight from STG.
Yeah.
So do you do something similar, or do you go through C++? What's the...
We go through CMM.
Okay. Cool, thanks.
More questions? Okay, it seems that all the questions have been answered. In that case, let's thank the speaker one more time. And we are free to stay in the room, free to hack on things. Cheng will probably stay here to help around. Otherwise, yeah, have a great rest of the afternoon.